Periyar Maniammai Institute of Science and Technology, Thanjavur. Think, innovate, transform.
Dear learners, this section we are going to see force, moment and deformation in a fixed beam under the course Mechanics of Materials. So, Mechanics of Materials deals with the failure mechanism of a material. That is, when a material is loaded, what are all the internal reactions that are taking place in a material. These internal reactions will be in the form of a shear force and bending moment. So, to calculate the shear force and bending moment, we are in a fixed beam we are going to see in this section. Before going to shear force and bending moment, let us see what is meant by beam and what are all the different types of beams. Beam is nothing but a structural member that resists lateral loads, and the deformation of the beam will be in the form of a bending. The total force that are acting on a beam will be produced shear force and bending moment, which are due to the internal stresses and strains and deformation which are acting inside it. These are the different types of beams: cantilever, overhanging, fixed, simply supported, continuous, and cantilever with a simply supported. In a simply supported beam, it is a type of a beam in which it is free to rotate and have no moment of resistance. The picture represents the simply supported beam. Next is a fixed beam. Both the ends are fixed and are restrained and have no restraint from rotation. The figure represents a fixed beam. Overhanging beam. In a overhanging beam, the beam extends beyond its supports on the one side or its one end. Double overhanging. The beam with both the ends extending beyond its supports on the both the ends. And continuous beam. Beam extending over more than two supports are called as continuous beam. A cantilever beam. A cantilever beam, one end of a beam is fixed and other end is free. One end is fixed and other end is free is called as a cantilever beam, and this picture represents a cantilever beam. One end is fixed and the other end is free. Shear force and bending moment. Shear force is nothing but an algebraic sum of all the forces acting on one or on the other side of a section. That is nothing but summation of all the forces acting on the section. And bending moment. Moment is nothing but force into displacement, and bending moment is nothing but algebraic sum of all the forces that are acting on any one side of the section. And why we want to calculate the shear force and bending moment in a beam? That is, when a beam is loaded, some of the internal reactions are taking place due to stress and strain. It leads to shear and deformation. The shear and deformation are represented in a pictorial manner for easy identification called shear force and bending moment. So, shear force and bending moment are helpful to analyze the structure for the structural design. This is the main concept for which shear force and bending moment is calculated. And this is a picture that is this is a crack pattern. When a load is applied over a beam, some of the internal reactions will be taking place, and due to the internal reaction, deformation will be taking place. And this is a flexural crack, and this is a shear cracks, and this is a combination of flexural and shear cracks. So, when in a simply supported, this is an let us assume this is a simply supported beam. When a load is applied over a beam, some of the internal reactions will be taking place. Before deformation, some of the internal reactions will be taking place, that is represented in a form of a shear and bending, that is in a pictorial manner. That is, when a load is applied, this picture represents shear is maximum on the either side and shear is 0 at the center. And this is the bending moment diagram. Moment is 0 at the either ends and moment is maximum at the center. So, these two, shear force and bending moment, represents where shear is high, where the moment is high, which will be helpful to identify or analyze a structure. While designing a structure or while designing a reinforcement detail for a simply supported beam, this shear force and bending moment diagram will be helpful to provide the reinforcement details. So, when a load is applied over a beam, some of the internal reactions will be taking place, and these internal reactions will lead to shear and bending. So, to resist the shear force, we are providing shear reinforcement, and to resist the bending, we are providing flexural reinforcement. This is the main concept for which why we want to determine the shear and bending in a section, and the shear and bending in a section is represented in a form of a pictorial representation called shear force and bending moment diagram. So, before calculating the theoretical concept of a shear force and bending, we want to go for some of the sign convention. That is, when a load is applied downward, we are assuming as a negative side, and when a load is applied in an upward direction, we are assuming as a positive. That is, either and vice versa also we can calculate. That is, you can also take upward direction as negative and downward direction as positive. For a bending moment, that is the hogging bending moment, two types of bending moment will be occurring. That is, one is sagging bending moment, other one is called as hogging bending moment. In hogging bending moment, if it is in a convex manner, the beam bends in a convex manner, that is, it is in an anti-clockwise direction, we are taking it as a negative sign. And for sagging bending moment, the bending moment, that is, it is in rotate, the beam rotates in a clockwise direction, and it is in sagging, we will be taking it as a positive, and vice versa also we can take, but we want to consider the sign convention. This is the nature of the shear force and bending moment diagram for and various load conditions. That is, two types of loads are there. One is called as a point load, other one is called as UDL. When an UDL is applied, the shear force will be in a form of a rectangular section. This picture represents the shear force and the pictorial representation of shear force and bending moment. When it is a point load, the shear will be in the form of a rectangular section, and the bending moment will be in the form of a triangular section. For an UDL, that is uniformly distributed load, the shear force will be in the form of a rectangular section, and the bending moment will be in the form of a parabolic section. This is the pictorial representation for easy remembering of shear force and bending moment diagram for various conditions. Let us take a simple example of a simply supported beam and it a point load and UDL. So for a point load, if this is a simply supported beam with a point load, when a load is applied over here, and this is a shear force diagram. That is, when a load is applied in an upward direction, that is, a resistance will be created. So the load will be extended here until the same load will be traveled here, and this point again an opposite load is applied, so resisting an upward direction will be there. So this load will be maintained till this end, and it will be in the form of a rectangular section. So shears maximum on the either side, and it is a 0 at the center. And this is a bending moment diagram. So for a point load, shear force will be in the form of a rectangular section, and bending moment will be in the form of a triangular section. So moment will be 0 at the either end. So moment is 0 at the either end, and it is maximum at the center. For point load, the bending moment will be in the form of a triangular section. For uniformly distributed load, the same, that is shear force will be in the form of a rectangular section, and the bending moment will be in the form of a parabolic section. So this shear force and bending moment diagram will be easy for identification, pictorial representation, which will be easy for identifying where shear is maximum, where bending is maximum, so that we can analyze the section easier for reinforcement details and other analysis. So we have two types of structures. One is called as a determinate, and other one is called as indeterminate structures. Determinate structure is nothing but the structure that can be analyzed using the static equation. That is, sigma v is equal to 0, sigma h is equal to 0, and sigma m is equal to 0. This is called as a determinate structure. For example, a simply supported beam is a determinate structure. Other is an indeterminate structure. In indeterminate structure, the structure cannot be analyzed only by using the static equation. That is, sigma v, sigma h, and sigma m is equal to 0. Alone with this static equation alone, we cannot analyze the structure. Then it is called as indeterminate structure. For example, let us take these two pictures. This is a simply supported beam. We can assume this span length as 2 meter. For a 2 meter span, this two supports will be enough, and the bending will be resisted. So the section will be safe. Let us assume the span of this section is extended from 2 meter to 10 meter. So the span length for this support is 2 meter, and we are extending this span length to 10 meters. When it is extended for 10 meters, the support, the beam will not be stable, or the section will not be stable, and so maximum deflection will be occurring at the middle. To resist the deflection, we are introducing two additional probes at the center. This is a structure which is, we are introducing additional support at the center. So by introducing additional structure or a probe at the center, what happens? The structure will be stable and the deflection will be get minimized. So this is a structure, this is an example, and this type of beam is called as continuous beam, and this continuous beam is an example for indeterminate structure. For determinate structure, this simply supported beam, we can take it as an example. And for indeterminate structure, to resist the deformation or to make the structure stable, we are introducing an additional props so that the structure is stable. This type of structure is called as indeterminate structure. Example is that is continuous beam. So in this module, we are going to see only for indeterminate structures. So example for indeterminate structures, continuous beam and the fixed beam. Now we are going to see the theoretical calculation for a fixed beam. Fixed beam is an indeterminate structure and we are going to calculate the shear force and bending moment value for a fixed beam. Let us take a problem. That is, theoretical calculation will be helpful to identify the values, that is maximum values for which the shear is maximum and the bending is maximum for a structure. So the problem indicates that a fixed beam of span 6 meter carries a point load of 150 kilonewton at a distance of 2 meter from each support. Calculate the reactions at the support, and we want to draw the shear force and bending moment diagram. Take they have given the E value and I value. That is, I is equal to 9 into 10 power 8 mm power 4 and E is equal to 200 kilonewton per mm square. This is the problem which they have given. That is, if they have not given the diagram, we want to draw the diagram. That is, if it is a fixed beam of span 6 meter, we can draw a fixed beam for a span length of 6 meter. They have given a point load of 150 kilonewton at a distance of 2 meter from each support. So from support A, 150 kilonewton at 2 meter, and from support B, that they have given us from each support. So from the other support B, 150 kilonewton for a span length of 2 meter. Since this is 6 meter, it is equally spaced. So 150 kilonewton from one end and 150 kilonewton on the other end, 2 meters, or the middle will be at 2 meter. If they have not mentioned the diagram, we can draw the diagram by the given data. So I am assuming the sign convention as downward direction as positive and then this is upward direction as negative. So first we can, that is, and then fixed beam, two reactions will be there. One is our support reaction, other one is a moment will be acting. So for a fixed condition, two supports will be there or two reactions will be there. For a fixed condition, two reactions will be there. One is a support reaction, other one is a moment. So reaction will also be there and moment will also be there. And now we am considering separating the reaction and the moment, and first condition I am taking it as for only the reaction. So first condition I am taking the first condition as only the reaction. Here only reaction RA, that is due to this condition, due to the support, an upward reaction RA and RB is acting. So we want to calculate the value of reaction for these two loads. For 150 and 150, that is 300 load, what is the reaction at A and what is the support reaction at B, we want to calculate. So I am taking the moment about either side. That is one side we can take. I am taking moment about B. So moment is nothing but force into perpendicular distance. So force is RA into total distance. I am taking moment about B. So RA into total distance. Total distance is 6. Upward direction I am taking it as a positive and downward direction I am taking it as a negative. So downward direction is negative. So minus 150 into the distance is 4 meter. So RA into 6 minus 150 into 4. Again another load 150 is there. So minus 150 into 2 is equal to 0. So I am taking the minus side on the either side. So RA into 6 is equal to 150 into 4 minus, that is on the other side it goes to positive. So plus 150 into 2. From this I am calculating the RA value, and we know the total load RA plus RB is equal to 300 kilonewton. So RA is 150, RB is equal to 150 kilonewton. So this first step we have calculated the reactions on RA and RB. RA is equal to 150 and RB is equal to 150 kilonewton. And next, for these simply supported conditions, we are going to draw the shear force and bending moment diagram. So shear force at point B is equal to, that is RB value is 150, it is in an upward direction. So we can take this as a neutral axis. From this axis, so RB value is 150 plus 150. So upward direction I am taking it as a positive. So from this point, 150 kilonewton is acting. So shear force at point B is equal to 150 kilonewton. This 150, next we want to calculate this point. I am taking this point as D. Shear force at point D is equal to, and we want to calculate till this point. So till here it is 150 and 150 is maintained till here, Again, I'm taking this as positive and downward direction is minus. So 150 kilonewton minus 150 kilonewton. Till here it is 150. Again 150 is acting in downward direction. Downward direction is minus. So plus 150 minus 150 is 0. So shear force at this point is 0. This 0 kilonewton will be travelled till this point. So till this point 0 shear force is acting. So from 0 again minus 150 kilonewton is acting here. So 0 minus 150 is minus 150 kilonewton. So this is a positive and downward I am taking it as a negative. So minus 150 till this minus 150 is occurring here. So minus 150 kilonewton will be travelled to this until this point. Here when it has come to this point, already here it is minus 150 and RA value is plus 150. So minus 150 plus 150 is 0. So this diagram will be ending here. So this is the shear force diagram. And similarly bending moment diagram. Bending moment is nothing but force into perpendicular distance. So here force is 150 but the distance is 0. So moment will be 0. So only we are telling moment on the either side will be 0. Moment at point D. Force into perpendicular distance. Force is 150 into 2. 150 into 2 is 30. Since this is a moment, force into perpendicular distance. Force is kilonewton and unit is a kilonewton meter. And similarly on the other side, moment at point C. RB into, we can take also RA into 150, or we can also take RB into 4 minus 150 into 2, that is 300 kilonewton meter. Similarly, bending moment at point A will be 0. So on either end the moment is 0 and here it is 300 kilonewton meter and here it is 300 kilonewton meter. We know that if it is on point load, bending moment will be in a form of an triangle. So the picture represented like this. So this is the shear force diagram and this is a bending moment diagram. So next, that is two conditions will be occurring in a fixed beam. One is the reaction, other one is moment. So for the 6 meter span, I am only considering the next step, I am considering only the moment. So to calculate the moment here, I am taking only moment. That is, we can take this diagram as an continuation. So moment MA into total distance 6 is equal to, it is in a form of a trapezium. So for calculating the moment, I am calculating in an area method, and we can consider this triangle. Area of this triangle is half base into height. Half into base is 2 meter, height is 300. And we can consider the second portion is length into breadth. That is, here it is 2 meter and the height is 300. And same for the third portion, half base into height, half into base is 2 meter and height is 300. So I have calculated here moment at A into total distance 6 is equal to first triangle, half base into height, second is a rectangular portion, length into breadth, and third one is a triangular portion, half base into height. So by simplifying, moment at A is 200. Similarly on the other side, if you are also taking, the moment will be the same because it is a span length is equally distributed, 2 meter, 2 meter, 2 meter. So the other moment will also be 200 kilonewton. So this is in a form of a rectangular section. Here the moment is 200. The 200 will be same till the other end. Here also it is 200. So now I am consolidating all the diagrams. So first I have taken it as a simply supported. For this simply supported moment diagram I am represented here. Other one is I am considering the moment. For the moment I have represented the moment diagram. Here it is 200, 200. While combining these two diagrams, bending moment and the moment diagram, I am combining to for a final bending moment diagram. This is first picture and this is the second picture. So this is 300 and this is 200 kilonewton meter. This is the final bending moment diagram. And in the problem they have asked us to calculate draw the shear force and bending moment diagram, and also we want to calculate the central deflection which is acting in a beam. So for calculating the central deflection in a fixed beam, the formula is del max is equal to minus 25. This minus sign indicates the deflection is in the downward direction. So this is the formula. So minus 25 into WL cube divided by 3240 into EA. So minus 25 into W is the load, 150 is same load. Both the section it is on same load. So 150 into span length 6 meter, 6 into 6 cube divided by 3240 into. In the problem they have given the value, E value and I value. E they have given us 200 kilonewton by mm square, but I am going to substitute for all the others. We have substituted at meters. So while substituting, it should be substituted in the same unit. Here they have given it as a kilonewton by mm square, but for all the previous calculation you have used the unit as meter. So I am converting it into meter. So 200 kilonewton divided by mm, I am converting into meter, and it is meter square. So it is a 2 into 10 power 8 kilonewton per meter square. And same I value they have given us 9 into 10 power 8 mm power 4. So mm I am converting into meter. So 9 into 10 power minus 4. 9 into 10 power minus 4. So the deflection value is del max is equal to minus, by simplifying we got the maximum deflection value del max is equal to minus 1.38 into 10 power minus 3 meter. So minus sign indicates the deflection is in the downward direction. Thank you. And the next section we can see for a fixed beam of unequal loading.
Periyar Maniammai Institute of Science and Technology, Thanjavur.